Okay, welcome to part 2 of the practice exam. I'm going to solve these last couple of problems here. So our first problem is we have Victoria driving her car on a straight road, and she stopped at traffic at a red light, and at time t equals 0, the light turns green, and Victoria accelerates at a constant rate until she is driving the speed limit, 40 miles per hour. Victoria drives a slow car, so it takes 1 minute to accelerate to top speed, and then she drives at a speed of 40 miles per hour for 4 minutes. After this happens, she slows down over the course of 1 minute to 0 miles per hour, and says she decelerates at a constant rate. So we're decelerating at a constant rate, and we are accelerating at a constant rate. Okay, so if we were to draw a picture, what it looks like is from a bird's eye view. Here's our car, and we're at a red light, and then we speed up for a little while. Speed up, and then we drive 40 miles an hour. And then we start slowing down. And then we stop. Okay, so if we want to draw a graph of v of t, now remember v of t measures the velocity of the car. Well, at first the velocity of the car is 0. And then once we get to the middle section, we're at a constant velocity of 40 miles per hour during this middle section from minutes 1 to minute 5. And then the last section we're slowing down, and then by the time we hit minute number 6, we have stopped. So the way that I want to interpret this information, which is in the problem, which says that we're accelerating at a constant rate and decelerating at a constant rate, means that the rate of change in these sections is constant, meaning that the derivative is constant, or in other words, the slope is constant. So during this first section, I know that I can fill this in generally just as the straight line which connects the 2 points. I know that at 0, I'm driving 0 miles an hour, and I know at 1, t equals 1, I'm driving 40 miles an hour, and I accelerate at a constant rate until I get to that point. Likewise, the last little leg of this here is going to finish out our trapezoid. Okay, so this is kind of the graph of what our picture looks like. So let me just go along with blue. Hopefully you can see while I'm going along. So I start at 0 miles per hour, and then as I inch my way up this thing, I'm speeding up, and then I hit top speed, and I hang out at 40 miles an hour for a few minutes, and then I start slowing down at a constant rate until I reach a stopping point. Okay, so that's how we can read this graph here. Okay. Something I want to point out is we should be very careful about what we do next, since v of t is measured in miles per hour. However, what we are given in terms of t is that t is measured in minutes. 1 minute to accelerate to top speed, drives at 40 miles per hour for 4 minutes. So we're going to have to be a little bit careful about the way that we put together this graph in order to say something about how far Victoria drives in 6 minutes. So in the last video, I believe I mentioned that we have, or not in the last video, in the what to know for exam 3 video, I mentioned that we should know the relationship between the velocity function and the distance function. In particular, the distance traveled. I can tell the distance traveled by looking at the velocity graph by measuring the accumulated area underneath this velocity graph, but we have to be careful with the units. What I need to take is I know velocity equals distance over time, so this tells me that distance is going to be equal to velocity times time. But it's not going to work out if I use miles per hour times the number of minutes traveled, because we can't cancel a minute with an hour. So what we're going to need to do is convert the number of minutes which we travel into hours, or else convert miles per hour to miles per minute. But I think the more intuitive thing is to convert these t lengths to match up so that we can say something about the hours, the amount of hours that we go that speed. And then we would be able to cancel these guys and we would just wind up with x miles. So that's what I'm going to do. Erase this stuff. In fact, I don't know why I don't just use this. That would be smart. Okay, so how far does Victoria drive in these 6 minutes? Let's handle each piece one by one. So here, the height of this triangle, this first triangle here, is, well, the area of a triangle is going to be 1/2 base times height. So what I'm going to need to do is measure this height here is 40 mph, and this length here down on my x-axis is 1 minute. So to find out how far I travel, I need to take the speed at which I was traveling, miles per hour, and the amount of time that I was traveling at that speed, which was 1 minute. And we'll worry about the units in a little bit. Let me take care of the next piece. It's gonna be this purple piece here. For this purple piece, I travel 4 minutes at 40 miles per hour. And I should have had a scaling of 1/2 here, 1/2, to find that area in terms of miles. And now I'll do the purple section. It's base times height, so 40 miles per hour. Miles per hour. And I will multiply that times the amount of time that I went that speed, 4 minutes. And lastly, I will add the green area. Again, we get 1/2 times 40 miles per hour. That's the height of this triangle, and the width of it is 1 minute, so times 1 minute. Okay, so now I want to actually compute what this is in terms of, hopefully I get some measurement of miles. So if I want to get a measurement in miles, what I need to do is I need to cancel these time factors. I have hour and minute, okay? And the way I'm going to do that is I'm going to make them match up. I know that 1 minute is exactly 1/60th of an hour, so I'm going to rewrite this whole equation as 1/2 times 40 miles per hour. And I'm going to multiply that not times 1 minute, but times 1/60th of 1 hour. Same thing with the middle, except I'm going to multiply by 4/60ths of an hour. And then I'm going to add 1/2 times 40 miles per hour times 1/60th of 1 hour. So altogether, I now can cancel my hours here, cancel the hours. And what am I left with? I'm left with 1/2 times 40, that's 20 over 60 is 1/3 mile, plus 40 times 4 is 160 over 60, 8/3 miles. Plus the last part, I'll take 1/2 times 40, that's 20, divide 20 by 60, I get another 1/3 mile. So all in all, I traveled, or sorry, Victoria traveled 10/3 or 3 1/3 miles. So what we did was we computed the area underneath the velocity curve, but we had to be careful to make sure that the units of length for the sides of our rectangle and the sides of our triangles matched up so that we could cancel out our units. Once we did that, it was a matter of doing a little bit of multiplication and a little bit of addition. Okay. So the last question, we're just asked to compute a couple of integrals. The first thing, we have a dead giveaway here. We have a large power on a polynomial function here. That's a dead giveaway that we should use U-Substitution. There's another dead giveaway, which is that we see the derivative here of the derivative of 3x cubed minus 1. This is almost like it out front. It's close. So this is telling us we should use U-Substitution, and it's an indefinite integral, so once I'm done I should wind up with a class of functions and not a number. So let's get started. I'm going to choose u to be the inside function, 3x cubed minus 1. If I choose that to be u, then du should be 9x dx. Now that's not exactly what I see. I've used up u equals 3x cubed minus 1, so that takes care of this inside piece, and now I have to worry about my leftovers. Now the leftovers here are going to be this 3x squared dx. And what I need to do is I need to make this right-hand side of the du equation look like 3x squared dx, and I'm going to do that by dividing both sides by 3. So I'll get 1/3 du equals 3, and this should have been an x squared, 3x squared dx. Okay, so now I have my u and my du, and all I have to do is replace. So I'm going to replace the leftovers by the thing which is equal to the leftovers. So I'll get the integral of u to the power 21 times 1/3 du. So that'll be 1/3 times the integral from u to 21, u to the 21st power du. And for that I get 1/66 u to the power 22, because I divided by the new power, which was 22. When I did that, I multiplied by the 3, which was already in the denominator. And now the only thing that's left to do is switch back to x. So I'll write this as 1/66 times 3x cubed minus 1 to the power 22. All right, so that's how we do that first problem. Oh, one last thing, plus c. Because remember, if I do indefinite integration, the end result should be a class of functions. Okay, so that's how we do that first one. Second one looks like it's going to be another U-substitution, and the reason is, if I were to rewrite this a little bit as the integral from 1 to e of ln of x squared times 1/x dx, then it's a little bit easier to see that this 1/x, oh, I meant to use the highlighter, this 1/x here is going to be the derivative of what's inside there, okay? In fact, 1/x dx, that's going to be our leftovers. So I'm going to choose u to be the thing which I see its derivative of in the integrand. So I'm going to choose u to be equal to ln x. And then du will be 1/x dx. So du nicely, perfectly matches up with my leftovers. I don't need to worry about messing with any constants, and I can just rewrite this integral. Now, I need to be a little bit careful about my bounds, so let's rewrite in terms of u first. I'm going to have u squared, and then I just need to write whatever's equal to the leftovers, which is 1 over x dx. That's equal to du. So I write du. And now the thing that's left to do is handle my bounds of integration. I'm going to use method, I think we called it method 1 in class, where I'm going to take these bounds here and I'm going to plug them in for x in this function which is equal to u. And then I'll have u values, and then I can just complete the problem with u. So it'll be ln of 1 and then ln of e. So let's rewrite that. I know how to do ln of 1, it's 0. And ln of e is the power of e, which when we take that power of e, we get e. Well, e to the 1 is e. So this should be the number 1 here. And then we keep u squared du. And now all we have left to do is finish out the integral using this. Okay, just need to do the integral from 0 to 1 of u squared du. It's simple as can be. U cubed over 3, and we evaluate at 0 and 1 because we're doing a definite integral, and we should get a number in the end. And that number is 1/3 minus 0 equals 1/3. So that's one way in which we can use U-substitution. The other way would have been to instead use x equals 1 and x equals e, and then once you got to this step, you would replace u by ln of x, and then you'd plug in x equals 1 and x equals e into the function ln cubed over 3. So that would be the second method, but we did it the first method, so why don't we just get rid of this stuff so that it's not confusing. All right. And lastly, we want to do this integral here. We have the integral from 0 to 1 of x squared to the power 10 dx. And this does look complicated somewhat, but I'm getting a feeling that we won't be able to use U-substitution for this problem because although I see an x squared which is in some weird power here, what I don't see present is the derivative of x squared out front. I'd be hoping to see something like 2x outside of those parentheses if I wanted to use U-substitution. So since I don't see a constant multiple of the derivative of that inner function being multiplied anywhere in our integrand, I'm thinking that U-substitution is going to be a poor choice for doing this problem. In fact, it's not going to work at all. So I need to be a little bit more clever with this, and hopefully by now you see what we're going to do. We're just going to rewrite this as the integral from 0 to 1, and I'm just going to take x squared to the 10th power. Well, if I take a power, if I take x times x, that's x squared, and I multiply it times itself 10 times, I'm just going to get x to the power 20 dx. And that's a problem that I know how to do. I can just take x to the power 21 and I divide by 21, and then I will evaluate at 0 and 1, and I will get 1 over 21 minus 0 equals 1 over 21. Okay, so that's how we do these integral problems. I hope you found this practice exam instructive. If you have any questions at all about how I solved any of the problems in these practice exam videos, I would really highly recommend that you come to my office hours or send me an email if you need to set up a meeting outside of office hours. I think I can make arrangements to meet with any of you guys if that's needed. So happy studying and good luck on the exam. Catch you next time.